And so hello and welcome students to this class, and this is course number MA412 linear linear algebra, and this is lecture number 21. Lecture number 21. Okay, and today we are going to discuss something called spectral theorem. Spectral theorem for diagonalizable operators. Okay, this is our today's topic, spectral theorem for the diagonal operators. Okay, so let me discuss what you mean by spectrum, other things. So I will discuss for finite dimensional case, obviously, and so let t belongs to LV, and we have this finite dimension. So now V is finite, something say whatever. Okay, so the spectrum is actually called the point spectrum in the case of finite dimension. Okay, the point spectrum of T is the set of all eigenvalues of T. Okay, so in general, and this is defined by sigma of T. Sigma of T. This is alpha such that T of V equal to alpha V for some V not equal to 0 vector. Okay, V belongs to V. But in general, this is in our case we are doing because we everything finite dimension. When you go to the when you learn next semester functional analysis, then you will say that this is actually collection of. In general, we will define sigma t is all those alpha such that t minus alpha I inverse not exist. So that means it's not invertible. Okay, and you see that this is actually subset. This is actually subset of this thing. So every eigenvalues for every eigenvalues is true, but complex is not true. So there are many. There may be many complex number for which t minus I, alpha inverse not exist, but that does not mean that that will be eigenvalue of t. Okay. So in our case, we will only consider on this finite dimensional case. In fact, in finite dimensional case, everything is only this sigma t is collection of all the eigenvalues. Okay. And okay, so we are going to discuss the decomposition of diagonal operator in terms of these eigenvalues, and for that we need a few more definitions. So definition. So we say that. So let uh, so be a vector space over a field F, an operator of an operator. So E belongs to LV is said to be a projection or projection operator if what happen E square equal to E. Okay, in this case we will say that E is a projection operator. Okay, and then we can actually write down, we can say that so let suppose R is the range of E, say EV means range of E, and N is the null space of E, null space of E. Then actually we can write down, then actually we can written as R direct sum of N. Okay, and that is obvious because so okay, so and obviously you can say that if suppose V belongs to V is in R the range if and only if actually this is implied by the image of V equal to V. Okay, so what does that mean? That means that when you so if it is in the range, then it under this projection operator will be under range on R, it will be same thing, and the null space means the image will be 0, right? So with this and obviously, and how the decomposition will go. So you write down any vector V in terms of EV plus V minus EV, and then you see that this is in the range, this is in the null space. So this is the direction decomposition, okay, of the vector space V in terms of projection operator. Okay, now for projection operators, there are few properties are true. We will prove this thing in terms of theorem. So I'll write down that theorem. And this theorem is also one important theorem that is going to help us to understand the spectral theorem. Okay, so what does that says? That suppose so if V is a direct sum of some operator, some subspaces. So I'm not saying that V is I'm not saying that the Wi is invariant or something, whatever. So it's some direct sum. Okay, then obviously then there exists K linear operators so let me write down the name, say E1 E2 dot ek on V ek, that element of LV. Okay, such that what happened, so the number one the EI is a projection. Number one EI means EI square equal to EI for all I equal to 1, 2, 3. So this all those EIs are projections. Number two is that whenever you take composition of EI EJ, and that will be Kronecker delta IJ. Okay, so rather no, I should not say Kronecker delta. Sorry. So it should be either EJ or that. So how do I write down? So when I write down the 0, if I not equal to j. If I equal to j, then it is EI square, but EI square equal to EI. So when the I and j are same, then it is EI itself, right? So yeah, so I should, that means so I can write down by this delta ij of EI. Okay, so yeah, so when j equal to I, then it is 1 and then EI. Okay, otherwise this you can say like this. And the sum of these EIs, so E1, E2, EK, the sum is actually identity operator. Okay, and not only that, the range of this, let me Ri is the range, so Ri equal to this range of Ei, and this has to be equal to Wi. So range of Ei's, which is Ei of V, which is also Ri, these are actually Wi's. Okay. And not only that, and conversely also, converse part is also true. That means if you have a operators E1, E2, Ek with all these properties, then that tells you that V can be written as a direct sum of subspaces. Okay. And conversely, if there exists if E1, E2, Ek belongs to LV such that Ei is satisfied all the properties, it is fine. All the above properties, properties, that means this 1, 2, 3 and 4, then actually you can write down, then V is actually direct sum of this W1, W2, Wk, I equal to 1 to k. The converse part is also true, and this theorem tells you that you can actually interpret the subspace in terms of the projection operators, which are nice to handle. Okay. Now you need the proof for this. Now, how do you prove this? It is given that W equal to direct sum of Wi's, I equal to 1 to k. Okay, and then you define your Ei's are mapped from V to Wi's. How you define? So, or rather, you can write down V to V. So this is mapped from V to V also, right? W is subspace of V. And how do I define it? So you're taking an V belongs to so for any V belongs to V, because V is direct sum of Wi, you can write down V equal to V1 plus V2 plus Vk, which is a unique, decomposition of V, right, in terms of element of Wi's, because this is the meaning of direct sum, in terms of elements of Wi's. Okay. So suppose this is given, and then what you can do, you can actually define your Ei. You can define your Ei of V is Vi. Now if you do this thing, what happens? Can you prove that this is a projection? So let us prove one by one. So to prove one, what you need to prove? You need to prove that E square of any i's is E itself, right? So we start with E square of, say, I of V, and that will be nothing but Ei of V, but Ei of V is nothing but Vi. Okay, and the way I define Vi belongs to Wi's. Okay, and then has to be equal to Vi, right? This has to be equal to Vi. Why it has to be equal to Vi? You don't need this also, is enough from here to here, because Vi is element of Wi's, and So vi can be written as 0 plus 0, and then only the ith position is vi, everything is 0, right? That is the unique thing. But from here, what you know, you get that, so you can vi, which is also ei of v. So that means that ei of ei square equal to ei. And this is true for all v, right? For all v belongs to v. It's true for all v belongs to v. So ei square equal to ei. This is also true for all i equal to 1 to k. There is no special about I here, right? You can choose any I. So what does that mean? That means EIs are projection, right? So EIs are projection operator. Projection operators. Okay. So so this first one is proved. Now second what we need to prove? Second thing is we need to prove that this EI EJ equal to 0 if I not equal to 0, right? So what is EIJ of V? So that you write down EI of VJ, okay. But when you write down, so this is what this is V in terms of V1, V2, and Vk, right? Now when you write down EJ of Vj, but Vj when you write down in terms of direct sum, then it will be nothing but 0 plus 0 plus 0 is ith position, say ith position. Then Vj, which is in the jth position, and then 0, okay. So this is a decomposition of Vj in terms of sum of elements of Wi's, and see the ith position is 0, so the image will be under EI, image of EI, this element under EI will be 0 itself, right? And that is true whenever I not equal to j. Okay, so this is if I not equal to j. Okay, and then what does that mean? That means that EI EJ equal to 0 if I not equal to j. Okay, so second property is proved. The third property was what? That the direct sum of EIs are actually identity, and that's obvious because for any V belongs to V, you can write down V in terms of V1 plus V2 plus Vk, right? And what is V1? So V1s are nothing but image of V, and so this VIs are what? VIs are nothing but E of VIs, right? E of V. So you can write in terms of, instead of V1 you can write down it is E1 of V. Similarly, next time will be E2 of V, and so on. The last Vk will be nothing but image of V under Ek, right? So what does that mean? That is true for all V. So you can write down that I. So V means you can write down that IV, right? IV equal to E1 plus E2 plus plus Ek, and then whole of V, right? And this is for all. This is true for all V belongs to capital V, and that implies that identity operator actually decomposes into the direct sum of, or the sum of these projection operators Ek. Okay, so this is the third proof, and the fourth one is the range. Obviously fourth one is range, that is by definition. So fourth one is true by definition, the way I choose. So Wi is that range of EIs. Okay, this is by definition. Okay, now conversely, if these all those things given, they will need to prove that actually then actually this is true, right? So conversely, okay, conversely, if E1, E2, Ek belongs to LV with all this property, all 1, 2, 3 and 4, then we have to prove that the V is direct sum of that. So obviously for any V belongs to V, you can write down that V equal to IV, right? Identity, but I is nothing but direct sum of E1 vector EK of V, right? So E is nothing but E1 of V plus EK of V, right? And hence you can write down V equal to, suppose E1 of V is V1 plus V2 plus Vk, where Vi is an element of Wi, right? So the one part is obvious that you can obviously write down the sum of vector space W1 plus W2, right? W2. And to prove direct sum, we need to prove that this expression is unique. Okay, so the expression is unique, then we are done. Now, so what do you mean by the expression unique? It means that suppose these VI's are also coming from another vectors, still the image of V under E, image of V under these EI's will be VI's only. Okay, that is the meaning of uniqueness here. Okay, so to prove the uniqueness, if I prove that this expression is unique, then we are done. Then that means V will be the direct sum of this thing, right? So you remember that is one of the condition of direct sum, right? If the unique representation, right? Now, so that uniqueness part is actually proved. So suppose that for that, so let us assume that these VI's are actually coming from some another vector, say maybe this is under Wi, right? So image of some vector. So suppose this is image of some vector UI's. For I don't know the UI's are same or not. But let me assume that this is UI for some UI belongs to V. Okay, and then also we will prove that still these are image under EJ. So if you start with say EJ, so what will be the image of EJ? Image of B under EJ, so that you can write down as sum over EJ, and then you know that V is direct sum of V1, V2, Vk, I equal to, so this is kind of okay, so I should not write down sum here, next line will be sum. Okay, so that means what? That means this is sum over I equal to 1 to k EJ of Vi. Okay, and these VI's are, I am assuming that the VI's are coming from some another vector, suppose. So suppose this is I equal to 1 to k EJ of EI of UI. Okay, these VI's are image under EI under some another vectors UI, and then we know that this EJ EI are also from property number 2. So you check what is property number 2, tells you where is that. Yeah, so this has to be equal to 0 unless, so this is 0 whenever I not equal to j, right? Whenever I equal to j, then it is same thing, right? So when I running over 1 to k, it will survive when I equal to j. So when I equal to j, it will be EJ square, EJ square of UI, right? But EJ square is what? EJ square is nothing but EJ itself, right? Because property number 1 tells you that this is EJ of UI, but EJ of UI is nothing but VJ. The way we find out EJ of UI equal VJ. Okay, but so what does that mean? That means that this, when you apply your EJ in V, the image of V under EJ is nothing but the VJ only, right? So all the vectors are actually coming from the same vector under this image. So that tells you that this is direct sum. So thus V is actually direct sum of this Wi's. I equal to 1 to k. Okay, this is if you want to know about subspaces, right? The question is that do you have some more extra properties or extra information on subspaces? Like what if the subspace is invariant? So I did not assume that this W is invariant under any linear operator anything. Now suppose I have a linear operator and I know that W V is sum of some subspaces, but I don't want to. I mean I don't know whether it is invariant under T or not. Then you have some properties, and next step tells you that. So theorem. So let so whatever is given already assume I am assuming that in terms of like E1, E2, E3, everything is there already. I am also assuming that you have a linear operator on V is a T, and suppose that your that V is the direct sum of say Wi's, and EI's are actually projection map from V to 1 to Wi's. Okay, this projection says that EI square equal to EI. These are all projection maps. Okay, this is given to me. Under this condition, I want to know that whether these Wi's are invariant under T or not, because invariant subspace has lots of properties, right? That we already know. So then this Wi's are T invariant and if and only, this is actually necessary in subspace in both conditions, if and only T commutes with this projection operator. So what does that mean? That means T EI is EI T for all EI, for all I equal to 1 to K. So there are K many linear operators. I am assuming W I equal to 1 to K. I must write down that. Okay. So it is enough to check that T is commuting over with this EI or not. That will tell you that T is invariant. I mean the W is invariant under T. Okay. And this theorem is actually very crucial observation to discuss our spectral theorem of this finite dimensional linear operator on finite dimensional vector spaces. Okay. Which are diagonalizable. Obviously, I am talking about diagonalizable linear operators. Okay. So proof. So how to prove it? Proof. So we need to prove both the side. So first we will assume that suppose T commutes with all those things, and then what happens? And then next will be T. Those are invariant. Then what happens? Okay. So let T of EI equal to EI of T for all I equal to 1 to K. T comes with all those EI, suppose I am assuming. And then I need to prove that Wi's are actually invariant under T, or Wj's are. Okay. So what I need to prove? So let I choose a vector. So suppose V belongs to Wj. I will show that the image of V under T is also element of Wj. Okay. So suppose I am assuming this thing. What is my goal? My goal is to show that T of V is element of Wj. Okay, so what is T of V then? So T of V, I need to show that T of V element of Wj, but T of V is what? T of V is nothing but, so we will use the fact that V is nothing but, so V is element of Wj means what? So that means image of V under Ej is also V, so this is nothing but Ej of V, right? Then Ej of V equal to V, right? Because V is Wj, Ej is projection of V, so image of V under Ej will be V itself. Now T is commutes with all the EIs, right? So in particular T commutes with Ej also, so this is nothing but Ej of T of V, and C, this is nothing but, so what does that mean? That means the image of TV under Ej is nothing but TV, and this implies that TV is element of Wj, right? because Ej only sends elements of Wj to Wj, and other than Wj it sends everything to 0, right? Yes, so that proves that this is true for all v's, for all v belongs to Wj, right? Because I assume v belongs to Wj is arbitrary, right? What does that mean? That means Tj is, Wj is T invariant, invariant, and this is for all j, equal to 1 to k. There's no speciality about particular j, right? Okay, so yeah, so that tells us that that one part is obvious. Whenever T commutes with all the projection operators, then the corresponding image of this projection operators Wi must be T invariant. Okay. Now conversely, so converse part also need to prove. So conversely, assume that what do you assume? So suppose assume that these Wi's are invariant under T. So assume that each Wi's are invariant under T. Okay. And we need to prove that obviously what is given that W is V is a direct sum of W's, that is given, right? So as V is a direct sum of the Wi's, I equal to 1 to k, then you can write down your V in terms of this E1 of V plus ek of V, because identity operator is direct sum of this E1 into ek, right? So you can write down these things, and hence you can write down that T of V will be equal to T of, say, E1 of V plus T of ek of V. Okay, so this is given. Now now what happens? So and what is given that these W's are invariant under T. So what does that mean? That means these operators. So this is element of W1. The next thing is element W2, and this is element of WK, right? And this is invariant under T means what? This invariant means that when we apply T, it will be again element, some element of W, right? So you can write down this is something, say maybe T1 E1, maybe E1 plus UK, where E1 equal to T of E1 of V element of, rather UI is element of Wi. Okay, and that is true because these Wi's are T invariant, and this is true as these Wi's are T invariant. So you can write down EI of V is element of Wi. So when you apply T, it will be again element of Wi, right? So T invariant. Now if you apply what I need to prove, that T is commutes to each of those EI, right? So now let me apply that EJ on this operator T of V. Then what happened? So T of V is this, so you can write down EJ of T of V, and that will be EJ of T, and then you can write down that, which is nothing but EJ of this U1, U2, UK, right? But now you see that this U1, U2, UK are element of U1 is element of W1 and UK element of WK. So the only thing will survive, which is UJ, right? Because other than that, so this will be EJ of UJ, Other than that, this as this ej of ui is 0 if I not equal to j, I not equal to j, because these ui's are actually element of wi, right? And now what is ui of ej? So ej is what? So now let me just do it. Okay, so uj, now write down what is uj. Uj is t of, so ej t of t of ej of v, right? Of v. Okay, so let me write down this. We use a t of ej of v, right? Now, so this vectors is element of w, right? So this is nothing but, or maybe I can write down here. It is nothing but uj itself, because uj is element of wj. So I don't need to write down this. Yes, but uj is nothing but this, which is nothing but t of ej of v. So what does that mean? That means you see that ej of t of v is nothing but t of ej of v is true for all v belongs to v, and that implies that ej of t equal to t of ej for all. This is true for all I equal to 1 to k, right? There is no special about particular one. And that tells you that your the linear operator T comes with every of these projection operators. Okay, so this is the proof. Now, under all those with all those properties, we are now going in the position to talk about the spectral theorem. So let me write down that spectral theorem for diagonalizable operators. Okay. So how to write down? So let me write down. So let t belongs to LV. I'm assuming this is from p fine dimensional, obviously. Otherwise, there is no meaning here. T belongs to LV is, or B rather, B diagonalizable, and you have eigenvalues, and say C1, C2, C1, C2, Ck's are eigenvalues of T, suppose. So what does that mean? So or other distinct eigenvalues, I should say distinct eigenvalues, because otherwise it's no meaning. So distinct eigenvalues. So distinct eigenvalues of T, and then what happened? Then actually there exists something. What is that? So you have linear operators. There exists u1, e2, ek. So that k coming from this k, whatever, how many such things are there, belongs to LV, such that something happened. What the thing happened? Number one is that these EIs are projections. This EI square, this EI is for all I 1 to k. Number two is Obviously this EIJs will be 0 if I not equal to j. And what is important, what number 3 is also same thing. Let me write down. You can write down I is in terms of sum of E1, E2 and EK. Okay, E1, E2 and EK, and the range of those EIs. Okay, so number 3, 4 are more important. 4 are fine. Number 4 is that T can be decomposed into something very nice. C1 of E1 plus C2 of E2 plus CK of EK. And not only that, number 5 is this range of EK, that um, Ri, which are range of E. So this range of EI of P, this is nothing of the eigenspace corresponding to eigenvalue Ci. So this is nothing but E Ci. This is eigenspace. Eigenspace of T corresponding to eigenvalue Ci. Corresponding to eigenvalue Ci. Okay, so this is the theorem. And not only that, conversely also, converse part is also true. So suppose converse part, so conversely if there exists, say, scalar, if there exists scalar C1, C2 and Ck belongs to the field F, and some non-zero linear operator, and this E1, E2, Ek belongs to LB, okay, such that which satisfied phi the condition that condition that Ej equal to, so this condition. So let me write down this condition, and then this condition and this condition. So 2, 3, 4 I should say. Then this one, number 2, number 3, number 4. Then obviously you can say that these diagonalizable, and those C1, C2, C's are actually eigenvalues for T, distinct eigenvalues. Okay, and condition rest of the condition 1 and 5 is also satisfied. Then with the all help of that, and T's diagonalizable. Okay, and the C1, C2s are Ck's are distinct DIS, DINC, distinct eigenvectors, eigenvalues of T. And not only that, also this condition with the 3 condition, other condition also true. Condition 1, which I assume that projections, so these are also projections, and condition 5 also true, that this Ri, which is range, this is nothing but E of Ci. Okay, also true. Okay, yes, so this is called the fractal theorem of diagonal operators on the finite dimensional vector space. And obviously the part is simple, so So there are two parts. So let me first assume that T is diagonalizable. Then what happens? So let T is diagonalizable. If T is diagonalizable, then what do you know? And obviously, I am assuming that this C1, C2, Ck's are distinct eigen values of T. Then we know that obviously you can define this W is a direct sum of and that we already proved. Diagonalizable means this is direct sum of C1 and so on Ck, right? So obviously so this is actually my W1, W2, okay, Wk. And you also know that the Wi's are invariant because eigenspaces are invariant. So these Wi's are invariant under T. That also you know, right? And now obviously you can now define your EIs are mapped from E to Wi's. How to define? So you take a vector V. You know that you can write down V. So for any vector V, you can write down as V1, V2, Vk. These Vi's are element of Wi's. So now you define image of EI equal to Vi. Now check that this satisfy all the property, whatever the property we write down. Okay. So it's already we proved that this satisfy the property the identity is equal to linear sum of that, right? So this V will be equal to V1, V2, Vk. Okay, and then once you apply T on this, that will be nothing but T of so the V1 is nothing but E1 of V, right? So E1 of V, and then T of Ek of V, right? This Vi's are nothing but Ei's of V. Okay, and and obviously because T is diagonalizable, so these eigenspaces are invariant under T, and hence if you commute each other, so this is nothing but E1 of TV and so on, Ek of TV, and they commute each other because T is because these Wi's are T invariant, and we just proved that in this case T is commutes with all those projection maps, right? But TVI is what? So this is C1V, because this is eigenspace correspond eigenvalues is C1, so this is C1V, so you can write down C1 E1 of V and so on, and then Ck Ek of V, right? This true for all V belong. I mean, if V is, if you write down V in terms of that thing, right? Or you can okay, so yeah, so this is true for every V. Okay, so so what does that mean? That means okay, so TV is actually element of W1, remember, and then you are writing this thing. So TV is also element of W1. Now you are just taking this. If B is an eigenvalue, eigenvector, then it will have this form, right? So what does that mean? That means T can be written as C1 E1 and Ck Ek, right? And what does that mean? That means you can write down T in terms of these projection operators with this multiple by the eigenvalues. Okay, and rest will be same because EIs are projections, so they satisfy all the conditions that identity are right. This part is obvious. Now we are going to prove the converse part, that so now conversely, so let T belongs to LV such that T they satisfy all those conditions. So what are the condition? So let me write down condition 2. What was the condition 2? This I think EIJs are 0, I not equal to J, and then Condition 3 was what? That identity is linear, right? Sum of this ei, ej, ek, and then condition 4 was t can be written of c1, e1 plus direct sum of, I mean the sum of ck, ek. With this, all those things, we can actually prove that t is diagonalizable, right? And obviously other two properties also. So now that is obvious because so now how do you prove number one, that is projection map? Now because you multiply by say ei, so you multiply by ei both sides, so ei of I is nothing but so so so, so this is so ei equal to ei of I, but you have okay, so I should write down the other way. Ei equal to ei of I, which is nothing but ei of this e1 and so on, ei of ei, and then ei of ek, right? But I know that only other than I equal to I, everything is 0, so this is nothing but ei square. So that means this is projection, right? This is the proof, first one. And also you can also prove that, okay, so now again it is given that t equal to say c1 of e1 plus dot 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 ck of ek. Okay, so if you want to so if it is multiplied by say ei, then what happen? Then you will have ei of t is nothing but c of ei square. Other than that, everything will be 0. And sorry, ci of ei square. So this is ci of ei. So what does that mean? That means that the image of t under that. Okay, so which also can be written as this t of ei equal to cei. So okay, maybe I can just multiply t by ei here, which is nothing but ce1 dot ck ek of ei, right? So that means what? That means you can write down t minus ei of I, this ei, this is ei equal to 0. So what does that mean? That means if you choose any vector here, so thus t of ci or I, this identity operator means ei of v for any vector, that is 0. So if some vector is image of ei, they are also in the null space of the, so that means this range of ei's are actually null space of this t minus ci of I, cii, right? So thus every non-zero, so these ei's are non-zero. I have assumed that non-zero ei's. Conversely, this is ei is non-zero. So for any non-zero element, in the range of ei's is in the image of is in the null space of so it is in the null space of t minus ci of v. So what does that mean? That means that ci's are eigenvalues of t, okay, and obviously eigenvectors are corresponding to eigenvectors ei of that v, right? Ei are corresponding eigenvectors corresponding vectors. Okay, so that part is obvious that the CIs must be eigenvalue in that case. And what more we know that also these so I need to prove that. So also we know that these E1, E2, EKs are actually 1. This is condition dependent, this identity. So what does that mean? That means any vector can be written as that image of these projection operators E1, E2, EK. But we just proved that this image is a projection operator as eigenvectors, right? So every vector can be written as direct sum of eigenvectors. They are actually eigenvectors. Eigenvectors of T. So what does that mean? Every vector can be written as direct sum of eigenvectors, and that means that thus V has a basis of eigenvectors. So T is diagonalizable. So thus T is diagonalizable. Okay. Now okay, so this is actually proof, and the CIs are the only eigenvectors that you can also prove that. If not, if there are some other eigenvalues, then what happens? So CI you can write down. So this is given that CIs are nothing but of this form E1 plus EK, CK, EK, and also identity is given by E1, E2, EK, right? So for any scalars, what happens is C minus T minus C of I, that will be nothing but, so multiply by C here, and then you will have C1 minus C of E1 and so on, right? For any scalar, CK minus CK of E. Okay, now I'm saying that if a scalar is eigenvalue, that means if this portion is 0 for some non-zero vectors, that means each of those has to be 0, right? And what does that mean? That means okay, so how do I write down? So you must have then, so if for some say non-zero vector V, T of Ci of V equal to 0, then what happens? Then that implies that C1 minus C of E1 of V plus dot dot dot, the whole sum is 0, right? Ck of C minus Ek of V, that is 0. The whole sum is 0. And I choose that V is not a 0 vector, so if that helps, what happens? So each of those is 0, so this is 0, this is 0, so everything is 0. So this Ci I can write down Ci minus E of Ei of this V equal to 0 vectors, and because V is not a 0 vector, so obviously so some of those has to be non-zero, so Vi is non-zero, so you can write down Vi equal to V1 plus something Vk. So at least it's not zero vector means what? That means at least one of those Vi part is non-zero, so Ei of V must be non-zero for some I, and that will be the eigenvectors for corresponding to eigenvalue Ci, right? So that implies that Ci minus Ei Vi is 0. With this is non-zero, so this implies C equal to C1. So what does that mean? Sorry, Ci. That means if there is any other scalar which satisfy the property that is the eigenvalue, there has to be one of those Ci's. So there is another option. So this Ci is the eigenvalue, and these are the only eigenvalues. Okay. So this is the proof actually that tells you that The moment you have t in terms of sum of these operators e1 into e2 in multiple of c1 c2 ck, then the ci must be scalar. This scalar must be eigenvectors for eigenvalues for t, and t must be diagonalizable. Okay, so this is the proof, and this is called the spectral theorem for finite dimensional for diagonalizable operator on a finite dimensional vector space B. Okay, so with this I'm going to stop today.